pushing this late. I think let's just get started and everyone else can kind of enjoy and hopefully not with too much noise as we go. Um, so we have a talk today about water contamination control from Scott Howard. So just a little intro. Scott is in his 24th year with High Pro Filtration, which is now part of the Donaldson High Pro. He has been certified for more than 15 years as both an STLE CLS and OMA. Scott began his technical career in 1991 when he enlisted in the U.S. Navy and entered the nuclear propulsion program. He was later selected to join the teaching staff at the Nuclear Power Training Unit in Ballston Spa, New York, where he instructed incoming nuclear power school students in nuclear propulsion and power generation fundamentals. 23 years ago, Scott developed High Pro's Filtrations Training Program, focusing on contamination mitigation and control, lab report analysis, system troubleshooting, and efficiency improvements. He currently serves as corporate account manager with a focus on system troubleshooting, system optimization, and industrial oil contamination mitigation, specializing in the control of particulate, water, acid, and varnish. Scott lives in Florida, where he enjoys the beach and spends time diving. He loves the outdoors, especially fishing, biking, hiking, exercising, and traveling. So thank you very much, Scott. We're happy to have you here today.
Thank you for that introduction. I appreciate that. I'd want to test to make sure. Can you hear me okay?
Yes.
Okay, good. I'm using AirPods. I just want to make sure that they're easy for you to hear. I'd like to start off by saying that this is an interactive type of presentation. I'd like to welcome anybody at any time to raise their hand or speak, and we will address your questions. If I could ask somebody to review the notes, if there's a chat spot where a question comes through, if you could alert me, I may not see it and I don't want to miss it. So
yeah, I'll keep an eye out for you.
Can do it. Okay, perfect. So without more delay, let's go ahead and get started. So this is just basically a picture of where we are outside of Indianapolis in Indiana. As mentioned, High Pro Filtration is now part of Donaldson Company. So Donaldson High Pro or Industrial Hydraulics. And today we're going to talk about water mitigation and control. This is not a sales pitch. This is more of, let's look at all the different options when it comes to all the different options as far as how you can address water removal and what the negatives are and what the positive are at each one, so that in your application, if you can, you'll be able to see which one is most cost effective. And so that's basically the goal here. Answer any questions when it comes to that. Okay, so just to jump in full speed, the differences in the three types of water in the system is the dissolved water is the first water that enters the system. The oil has solubility. And so as the oil dissolves the water, you'll see the percent saturation of the oil increase if you're testing it. And then once the oil has reached saturation, which is temperature dependent, so as the oil heats up, it increases the capacity to dissolve more water. As it cools off, its capacity drops. But at a fixed temperature, as water enters the system, oil will dissolve the water until it reaches what we call saturation. And at that point in time, any more water in the system will be considered free water. And then emulsified, the way I like to describe it, is free water that's been blended with the oil. And so that's important to distinguish between the three, because some of these technologies will not address all three forms of water, and that needs to be recognized. So I just wanted to go ahead and mention that on the front side. Any questions on these three? This is pretty basic at this point. No? Okay. So this is basically just a few of the different water percentages that's in oil, and using the bars behind the vials kind of tell you what you can see through or not. So I would like to distinguish the difference between the percent saturation of the oil and the percentage of the system itself. When we're talking percent saturation of the oil in parts per million, if the system, for example, is has 10% of the entire system as water. On a parts per million aspect, you have 1,000,000 parts per million, 10% of that is 100,000. So if we say the system itself has 10% water in the system, it's 100,000 parts per million. If you're looking at water in a relation to percent saturation at 10%, well, that's in relation to the capacity of the oil to dissolve water itself. So if your oil has a saturation point of 100, we'll use that for simple math, and your saturation meter comes back and says that you're at 10% on the saturation meter, that means 10% of the saturation capacity of that oil. And so that would be, in this case, 10 parts per million. So looking at this slide here, this is based on the total system. So on lab reports, you'll see if a Carl Fisher titration is used, and we'll get into the different methods here shortly. And it comes back and it says 1% is water, then that relates to 10,000 parts per million. So the easy way I like to describe that, if you forget, you say, well, what does 0.05% mean? Start at 10% from a million, 10% to 100,000. Move the decimal one spot to the left. 1% would then be 10,000. 0.1% would be 1,000. 0.01% would then be 100. So they kind of give you an idea. Any questions on this? Make sure that when you look at your lab report that it does read either in parts per million or percent saturation. And we'll talk about some of the limitations of other methods outside of Carl Fisher that are not going to be as comprehensive in giving you that data. So water contamination causes all these problems. One of the most important is viscosity change. That's the number one parameter of oil. So we want to make sure the viscosity is right. It does affect that. It also causes oxidation. It can also lead to additive depletion. And in some oils, like a phosphate ester, it can directly result in acid production. So water is something that we consider a contaminant and that has to be mitigated and controlled. All right, so when you look at this slide here, corrosion, 25%. So 75% of the reason your component loses usefulness is surface degradation. Of that, 25% of the reason surface degradation occurs is due to corrosion. So that's why water is so important. So you have mechanical wear particles and you have water. Those are the two top contaminants when it comes to surface degradation and then loss of usefulness of components. So detecting, removing, preventing water contamination. So here's the different tests that we want to describe and where the limitations are. There may be some differences of opinion within the people here today as far as the exact range, and I totally respect that, but this is kind of a general idea. So infrared, greater than 1,000 parts per million, it's accurate. Less than 1,000 parts per million, it becomes limited. So if infrared is used, like it's really good to determine if there's coolant in motor oil, but on hydraulic oil or turbine oil or gear oil, it's not as useful because we want to know, do you have free water in your oil? And if your oil saturation limit is at 200 parts per million, for example, and let's say you do have free water and your actual parts per million of water in the system is 300 or 400 parts per million, FTIR would show that that's negative. And so the lab report wouldn't indicate that you have free water. So we want to make sure and know that. So this is limitation with FTIR when it comes to hydraulics, turbine oils, compressor oils, and gear oils. Crackle test has a limitation as well. So for people who aren't familiar with crackle test, it's a metal plate. We heat it up, we put a drop of oil on it. If water is present, it's going to flash to steam or crackle. And that's where the term came from. Below 500 parts per million, you can periodically see some crackling occurring, but it becomes less and less accurate. So you could, in that scenario that I provided earlier, the 200 parts per million of saturation, you could have 300 parts per million of water. So you have free water, and crackle test may not show that. So there's a limitation there. Chemical reagent is the same way. There's two aspects here that we're concerned about. One of them is the health and safety concern. The chemical reagents can be rather challenging to your health. And so it needs to be addressed or at least recognized. And then the limitation as well. When turbine oil, for example, has a saturation point that could be as low as 100 parts per million or even lower, chemical reagents can be limited on the ability to show you if you have free water or not. RH sensor. Now, this is something I'd like to talk about here. We're going to get into a little bit more detail when it comes to the different systems that can be in use. A relative humidity sensor is one that measures basically the conductivity of the oil, or the opposite, which would be the resistivity of the oil in a system, and it's only based on on dissolved water. So in that scenario I used earlier, 200 parts per million, if I have 300 parts per million of water, the relative humidity sensor is going to read 100%. It's at its saturation point. It says, okay, we're at 100%. It's not going to go above 100%. So you're limited in your ability to actually know the actual volume of water in your system. Now, the RH sensor is used in vacuum dehydrators quite effectively because bearing manufacturers, the L10 end of life testing is based on 100 parts per million. So that tells us that the bearing manufacturers are interested in dissolved water. So we feel like relative humidity sensors are very effective on vacuum dehydrators because we want you to drive your water content down to where you have no free water, no emulsified water, and you're working on dissolved water. This is when the relative humidity sensor comes into play and works very effectively, but it cannot tell you total volume of water in your system. So we have to recognize the limitation. That's where Carl Fisher comes in. Carl Fisher can, the titration can go as low as less than 10 parts per million up to over 150,000 parts per million. So we have that ability to be able to show the big range of water volume in the system, whether or not you have free water. So I'd like to take this moment to encourage you to consider, if the lab you're working with isn't using Carl Fisher titration, or you are a lab and you have these options, recognize that whenever in turbine oil, gear oil, hydraulic oils, we want to be able to know the parts per million, even if there is no free water, or if there is free water. Carl Fisher is the one that we recommend that you consider using on a normal basis for your lab reporting. At this point, I'd like to stop and ask you, are there any questions on the test methods? Oh, okay. 5 technologies to mitigate and control water. We're going to go over water absorbing filters, the positives and negatives, desiccant trap breathers, coalesce products, vacuum dehydrators, and headspace dryers. So this is an example. I'm using one of my filter elements as an example. This is a water absorbing filter element. A couple things I need to point out for this. It's a consumable product. It will only remove free water. It does not address emulsified water. It does not address dissolved water. It's a consumable product that in some situations could be the most expensive option. It is not always recommended. So for a very small system, let's say you have an ID fanned gearbox and just a few gallons of oil, you want to remove some water, some free water out of that oil. What I'm going to ask you is 3 things. What's the volume of oil? What's the volume of water? And what filter element do you prefer to use to absorb that free water? Then I can do a calculation and let you know on the front side how many filter elements you expect to need to remove that free water. So then you can do an analysis and determine, well, do I want to do that, or do I just want to dump the oil and that oil that doesn't have free water in it? So to review on water absorbing filter elements, they reach a capacity. Now, how it works is there's several layers of filter media. So you've got like a sandwich. You've got backers before and after the actual media, and then you would have maybe 2 main layers, maybe even a pre-filter layer. When you go from dirt only to water absorbing, one of the main layers is removed and a water absorbing layer is added. That water absorbing layer will then swell, think of a diaper, as the free water is collected. And then it is contained within the filter element because of the other layer in there. How you know when you're using water absorbing filter elements that it is filling up is differential pressure. So differential pressure is how you determine when this filter element has reached its capacity. We recommend you don't use a very tight filter element when you're removing free water because it's also filtering dirt. And so you want to be able to focus on free water removal. That's how it works internally. Free water only, consumable, so can be the most expensive option, but also can be the most effective option for small systems. Any questions on this technology?
Can these just be dried after, or they're straight to the landfill?
Yeah, straight to the landfill. Think of a
Okay.
diaper that's not a reusable, like the traditional cloth diapers. These would be single use only.
Okay.
Hi, Scott.
Good
I got a
question.
question. So you said that DP is what tells you you need to change out your element on a water absorption element.
Correct.
So once it's holding 5.8 liters, for example, on a 36-inch element, it will DP out.
Yes, because as it swells within the filter element, it starts resisting flow through the filter element, and your differential pressure will rise to show that it is starting to swell and restrict the oil flow through it.
Okay. Thank you for that.
Yep, welcome. And you can see if it starts to plateau and you're reaching a certain DP and it's not going any higher, you probably already reached your water absorption capacity. And if you have more free water that needs to be removed, that would be the time to remove that filter element and put a new one in.
Okay, thank you.
Welcome. Any other questions? So that's water absorbing. And just to say again, it's not restricted on which oil you can use, but it's restricted to free water only. Okay, so the next one is coalesce. I should say somewhere in this slide that this is coalesce technology, but this is coalesce. So for fuel oils like diesel fuel, coalesce technology is one of the most recommended ones. Let's say diesel fuel has, let's say, 7 centistoke on average. So it's thin. Coalesce technology is very effective in one pass shedding of water. Limitations, free water only. Okay, so that's something that you have to recognize with coalesce technology. It's limited to free water only, and I'll get into the mechanics of how it works. It's also restricted to what I say non-aggressive additive packages. So the aggressive additive packages like the anti-wear, the extreme pressure additive packages will adhere to the filter media, and we'll get into that shortly. It will adhere to the filter media and it will render the coalesce technology useless. It will negate its ability. So anti-wear and extreme pressure additives, hydraulic oil, gear oil, you cannot use coalesce technology on it because the additive will adhere to the filter media and cause it not to work. Now, coalesce technology is only free water. So I get a question often saying, well, can it work on hotter oils? Well, sure. I like to use 130 degrees Fahrenheit as the fulcrum, above which I recommend vacuum dehydration, and below which I recommend coalesce technology if you want to use coalesce technology. But remember, it's only free water removal. So why do I have the limitation of 130? It's not because above 130, the media would be damaged. It's because above 130, your oil has higher capacity to dissolve water, and you don't have as much water in a free state that can then be coalesced and separated. Does that make sense?
Mm-hmm.
So 130 is kind of the number. So 120 is better than 130 for coalesce. 110 is better than 120, and so far down to, let's say, 80 degrees. At some point in time, the viscosity of the oil will become a factor just because it's thicker and it causes a differential pressure across filter elements. But the way this works, and here's kind of a fancy way, if you have heaters for some coalesce capabilities, like let's say turbine oil or paper machine lube oil. I would not recommend coalesce and paper machine lube oil because of the viscosity. So let's go back to turbine oil. You may use heaters to start up the system, then you don't need it anymore. The first thing we do is pre-filter with a dirt filter. We want to do that before it gets into the coalesce housings, because these two stages, coalesce and separation. I'll go to this. Here's your pre-filter. Coalesce and separation. These elements can be expired quickly by dirt. So we want to keep the dirt away from the coalesce and separator elements. If we can, theoretically, these filter elements can last a year, 6 months. It can last a long time until silt starts to build up in the coalesce and separator elements and render them ineffective. So that's why we pre-filter stage 1. 90% of the water will be coalesced in the first stage, the coalesce, and then the other 10% will be polished. How it works is basically it's using polarity to attract water droplets to each other. So in the tank itself or in the coalesce housing, you'll see water as it comes in will go through, let's say the white will go from inside to outside. As it goes through this white media, the water beads will start to form larger droplets and then literally start falling down with gravity into the bottom of the housing against the flow of oil. So inside to outside, and then through here it goes outside to inside through the green polishing media and then out of the system. We don't want you to touch this green media with your hands or anything really in particular, because the oils on our hands will cause the part of it that we touch to be useless as far as oil water's coalescing. So coalesce media or coalesce technology, pre-filter first. First stage coalescing water is the coalescer. It attracts the water droplets to each other. They form bigger droplets. Gravity drains them to the bottom. And then the second stage is polishing. You'll see a sight glass on the side. You can manually remove water by a valve when you see the level is reached a certain level, or you can have an automatic system that senses that automatically. If you have an automatic system, we're going to have that valve reshut when there's still water at the bottom of the sight glass. And the reason is we only want to drain water out the water drain and not oil. So we stop it at that point in time. So this is coalesce technology. You're limited in viscosity. I would not go above 100 centistoke. So a compressor oil is capable. Turbine oil is capable. Diesel fuel or fuel oil, you're capable there. That would be basically the limitations as far as viscosity. It's limited to basically like a turbine oil has a rust and oxidation inhibitor only. You can't use it on anti-wear and extreme pressure. The other limitation is only free water. Now, what's the advantage? Fast water shedding. In one pass, we can go from 5,000 parts per million to 100 parts per million in one pass, if that's all free water. So fuel oil inline supply, let's say you're supplying a diesel generator, for example, that fuel oil in one pass through a coalesce setup can remove your virtually all of the free water in one pass. So the advantage is fast recovery. If you have a turbine that let's say a steam turbine, that a lot of water entered it during startup as the labyrinth seals are heating up and sealing, that's when you have a water injection, pretty common. This will remove the free water extremely fast. But there are limitations. Free water only, 100 centistokes max, and no AW or EP additives can, you can't use it on those oils. Any questions on coalesce technology?
There may be a quick one, Scott. Is there any automatic systems for draining the water?
There is. Let's see if I have a picture of it here. So you can have an automatic system like a float or a sensor that senses the water level, and you would have basically once it reaches its high level, it would automatically open the drain solenoid, because the coalesce system operates at a low pressure, 25 to 50 psi, by simply opening the electrically operated, normally closed valve. By opening that, you're pushing the water out through the drain line until your float reaches the low level, then it would reshut that valve. The other option would be a manual valve and just a visual from a technician. Any other questions on coalesce? Okay. There's another example. It's in marine. We have a two-stage in one setup where basically it would be the same concept. So two inner core tubes that would go inside to outside here, and then outside to inside to the inner core tube and out. And this would be before and after in one pass. It works very well. Another example. So where you can use coalesce, you're limited to free water only, but it's fast for shedding the free water. So just remember the disadvantages and the advantages of this technology. Now we're going to talk about vacuum dehydration. Vacuum dehydration is the one that's basically, it does not care what additive you use. Anti-wear, extreme pressure, RNO, no additive like a phosphate ester, doesn't matter. Viscosity doesn't matter as either. We currently have vacuum dehydrators on up to ISO VG680. We do have one on 1000, which is very rare, but it can be sized properly for very thick oils as well. So what's its limitation? Well, it takes energy. So the energy, you have to hook it up, and we have heaters, and we'll get into that. And you can see them, kind of the heater tubes here. But what we're doing is we're flashing water to a vapor. We're flashing water to a vapor at a temperature that the oil will not be damaged necessarily. So we're going to pull a vacuum. By pulling a vacuum across the oil, we can then flash water to a vapor, not at 100 C or 212 Fahrenheit, but maybe at a much lower temperature that is more pleasant for the oil. It doesn't cause increased or rapid oxidation. 130 Fahrenheit, 140 Fahrenheit, maybe 150 Fahrenheit. You're not limited on your viscosity. It will remove all free water. It will remove all emulsified water, and it will remove a significant portion of the dissolved water. Where it's limited, comparing it to coalesce, it's if you have a water ingression event, it's not going to remove the free water as fast. So that's something that just take in consideration, that if you have an upset, you need to remove your free water. It's going to take some time. And that's normal because we're using vacuum and heat. So we're going to heat up the oil. We're going to pull a vacuum, and we're going to flash the water to a vapor, and then we're going to remove it. So how it works, basically, at least for our dehydrator, we use vacuum to pull oil into the system. Goes through the heaters first, then into the vacuum chamber. So the vacuum chamber here has dispersal elements. So this dispersal elements would be on a manifold. The oil travels from inside through the media, outside and down. The one reason why we send oil through the vacuum chamber, the dispersal elements, is to break the surface tension of the oil, so it's easier to remove water. It's easier to flash water to a vapor when you break the surface tension of the oil. And that's the sole purpose of the dispersal elements in the vacuum chamber. We have a vertical one because in our design, the water, as it flashes to a vapor, we have the, it goes up and it is entrained in the air flow. So here's the inlet air breather. It's pulled through the top, through the condenser, and into the condensate pots. As the vapor is pulled up, it is entrained in the airflow and removed from the system. What we recommend, it's just a design preference. There's other companies that like a horizontal design. We like the vertical better because we feel like there's more capability for surface tension breaking because we have so much surface media here. Also, this design is set to remove the top lid and pull the dispersal elements out and replace them. How you know the dispersal elements need to be changed is you can't maintain oil flow. So we use a positive displacement discharge pump and vacuum. So we're constantly pushing out the oil at a fixed rate. If these dispersal elements start to clog, we can't pull oil in fast enough with the vacuum to keep up with the positive displacement gear pump. And so you'll see your oil level drop out of sight. That's how you know these dispersal elements need to be changed. They're around 30 micron effectively for the thinner oils. And that would be up to and including an ISO 220 oil. Above ISO 220, we would recommend going with more loose dispersal elements like a wire mesh or even a packed element. Because we can go up to ISO 680, you really need to have more coarse dispersal elements in the vacuum chamber, or you can't pull the oil in fast enough to keep up with the positive displacement pump. So they're not there to filter dirt. It's there just to break up the surface tension of the oil so water can be removed. That's the reason to have these dispersal elements. And then when the discharge pump is pushing the oil back to the system, you go through a high efficiency filter. In some designs, in most vacuum dehydrators, you're going to have recirculation lines on a cold startup. You can, or a very high water content. You open this recirculation line, and after it goes through the entire process, the dehydrator, a portion of the oil that's been heated and polished can come back in through the system for additional water removal. That's why we put a flow meter here so you know how much you're diverting back for recirculation. So to review, vacuum dehydrators require heat and vacuum for their function. So you have to be able to heat your oil. If you have a heat exchanger on your system that's going to limit your system to 130 Fahrenheit, for example, that has to be taken into consideration because the oil has to be heated and a vacuum has to be pulled. Now, if people routinely ask me, they say, well, I don't have any limitations on the oil temperature or the vacuum. What do you prefer? What I prefer is go as hot as you can and touch base with your oil supplier to make sure that you're in alignment with your oil supplier on the max temperature that is recommended and lower vacuum versus high vacuum and low temperature. And the reason, the best analogy I can give is for people that are my age, you remember when McDonald's, for example, went from the small straws to the big straws. And that's so you can drink your soda faster and you order the big gulp or the larger soda. But if you use that analogy of the straw, it doesn't take as much effort with a bigger straw to pull the soda up into your mouth. And so with vacuum, it is a dual purpose. You're flashing water to steam or to a vapor, but the vacuum itself is also an indication of airflow. The higher the vacuum is accomplished by me reducing or shutting down on this needle valve to causing a higher restriction. So I can get a higher vacuum by shutting down on the needle valve. But what that does is that reduces your airflow rate. And the only way you remove water out of the vacuum dehydrator is the airflow. So perfect vacuum, 30 inches, we can flash the water to a vapor all day long. But if there's no airflow, that water is not being removed. So if I don't have a limitation on oil temperature and vacuum, I want to use as low a vacuum as I need to be able to flash water to a vapor. So I have highest airflow and the faster water removal out of the system. I've thrown a lot at you right now on vacuum dehydration, so I want to take a moment to ask, are there any questions on this technology?
Yeah, Scott, can I get just a quick, I'm more familiar with the horizontal ones where the diffuser disperser elements are in the top and the oil's in the bottom. So what would the oil level be in the vertical one? I assume there's not much oil inside there.
So the oil and the vertical one are going to be right around the middle of the sight glass, and that
Okay.
will be below the bottom of the dispersal
Disperser elements,
So,
yeah.
yeah, and so
Okay.
in this design, the entire dispersal element will be above the oil flow or the oil level. And so then theoretically, you can use the entire dispersal element for breaking up the surface tension of the oil. You'll notice that on new dispersal elements, the level is lower. If you look in through the top viewing window and see that oil will be cascading, let's say only a third of the way up on new elements. And as they start to collect particles, again, like I said, around 30 microns, so it's not there to collect dirt, but some will start to build up over time. You'll start to see that oil cascading, building up, building up, building up, to where eventually you get to the point where you're restricting flow and then you can't maintain it in your sight glass. But to
So-
answer your question, in the vertical, the oil level will be maintained below this dispersal elements.
And you monitor them by how high up the water's coming out rather than DP?
That's exactly right. Because you're only going to have two indications. It's not differential pressure. You're going to see where the oil level is cascading out to give you an indication that soon you're going to be to the point where you can't pull oil in using vacuum fast enough to keep up with the positive displacement pump. And then you will start to lose your oil sight glass out of sight low. And then in most dehydrator designs that are like this, you'll have an oil flow sensor that senses if you lose oil flow, it'll shut down the entire vacuum dehydrator. The reason is we don't want the heaters to continue to coke oil if there's no oil flow. And so it shuts down the entire system. If that happens more than once, then in rapid succession, like if I start it back up and it shuts down again because I can't maintain oil level in the sight glass, that tells me the dispersal elements are clogged and need to be changed. Theoretically, they should last once a year, where you shouldn't have to replace them once a year.
Scott, hi. We have a Mary raised hand for question if you have time.
Sure.
Yes, Scott. I just would like to know how many different dispersal elements you have in your design.
It depends on the flow rate of the dehydrator. We have the smallest, the 1 gallon per minute dehydrators. We'll use one. And then in this one in particular that has 4, this would be typically like a 20 gallon per minute dehydrator. So that is directly related to the flow rate of the system itself. The largest dehydrators that we make are 100 gallon per minute. And I'm going to have to speculate, but I think there's 8 dispersal elements that are in that vacuum chamber. So it's solely dependent on flow rate of the system.
Okay, thank you. But dispersal elements is going to be changed. I mean, the material itself is all same material. It's just different column, as you said, depending on the flow.
The material itself, it's a combination of it's a synthetic material. It's there just to break up the oil surface tension, so it's nothing really fancy. But we do have the option of stainless wire mesh. It's not quite as tight, and so it's a little bit looser. It's more designed for the ISO 320 and the ISO 460 oils. Some ISO 220 oils that may not thin out too easily, that have a tighter range as far as viscosity for temperature change. And so those would be stainless wire mesh. And then for the thickest oils, it would be stainless packed, like almost like you're just putting pieces of metal inside the filter element just to allow oil flow through, the thick oil through, but to have some effect on oil surface tension degradation. So the tighter the element, the more efficient in water removal, but the limitation on the viscosity as well.
Okay, thank you. I think we are going to contact you for more technology details because Darlington is interested in purchasing those vacuum dehydration units for FRF control. The water control in the summer is pretty high and 1200 ppm. So we want to have this VDU installed. So that's really interesting for us to know this technology. Thank you.
You're welcome. And the dehydrator should be sized to the system and to the water ingression capabilities. or assumption. If it's a dry system and it's not that large, you don't need a lot of flow rate. And so, for example, I'm going to pick on paper machines. Let's say I have 5,000, 6,000 gallons of paper machine oil. I can use a 20-gallon per minute vacuum dehydrator easy. For boiler water feed pumps in a steam turbine that maybe have 100 gallons of oil, a 1 gallon per minute vacuum dehydrator will be just fine. So it's not necessary to go with more flow rate for the vacuum dehydrator, because then you have to build a much bigger system. It takes a bigger footprint, and it obviously costs a lot more money up front. So the dehydrators should be properly sized to the system size and to the application of that system as far as water ingression expectations. One other thing that I was asked to bring up is, when would I want to pre-filter oil before it comes into a dehydrator? If it's a very dirty oil environment, and let's say you have the potential for a lot of contamination, if you're recovering oil out of a sump or a basement, for example, we would recommend putting a bag filter housing on the inlet. Okay, so the inlet here, we would pull oil through the bag filter before it goes into the vacuum dehydrator. You have to remember, though, that since you're on the inlet, you can't go too tight, and we wouldn't recommend two filter housings in series with bag filters, because you can restrict flow in the same way you can restrict flow here and not be able to keep up with the discharge, the positive displacement pump. But those applications, we do on occasion, we'll put a bag filter on the inlet. So that is recommended, that if you have that application where you are trying to reclaim oil, go through a bag filter first before you go through your high efficiency filter element, because these are expensive, bags are cheap. Any other questions on vacuum dehydration?
Thank you.
Welcome.
Yeah, Scott, Peter Hartenveld here. If you use the bag filtration for very dirty oils, what kind of micron rating do you use?
You can use 3 micron. You can have the capability of even trying 1 micron. Because bags are so cheap, you can try one and see if it can keep up, if the system can keep up with the restriction through the bag filter itself. And if it's a little bit too tight, then you can switch it back out to 3 micron. But we see that pretty common 3 micron bags. It's not a beta 4000 efficiency of a high efficiency filter element, but it still has the ability to catch particles down to that size. So yeah, you can go with a 6 micron or 3 micron bag as well.
Thank you.
Welcome. Any other questions? Any other comments on vacuum dehydration? Any experiences anybody wants to share? Okay. I'm getting close on time, so I want to talk about another technology real quick. Headspace dryer. Headspace dryer is very effective. So consider like a gearbox. So I'm going to take a dry air. Now I'm going to say this is a positive air flow, but not a positive air pressure. There's a distinction there I want to make. We have 1 CFM, for example, of air flow. I want to direct it on above the oil level in a system, and then exit through a desiccant breather. The reason I say exit through a desiccant breather is this super dry air will actually dry out your desiccant. So a technician or an operations person can walk by and visually check the color of your desiccant breather, and they know that your headspace dryer is working well. So the way this works is it goes through a membrane. Super dryer, we recommend compressed air. We recommend instrument air and not shop air, is what I meant to say, because the instrument air is cleaner. But then you do go through a filter regulator, an FRL, to remove the dirt and remove the oil as the water then goes in. So we're dropping the, I can't remember the term, it escapes me, but the vapor point, or maybe it's the dew point of the air. So naturally what nature tries to do is reach equilibrium. So if I have super dry air that I'm sending across the top of the oil level in a gearbox, for example, the oil will release the water into the air to try and reach an equilibrium as far as humidity. Okay, so this is how this works. There's no moving parts. It's brilliant. It works very well. And you can use one of these membrane dryers or headspace dryers for multiple gearboxes. What I would recommend is for example, a floating ball type regulator that shows you your airflow rate in front of each gearbox. And you can tee this off into multiple gearboxes depending on their proximity to each other. So you don't need one of these devices for each one of your gearboxes. You start with as low airflow as possible and start testing your oil. You do that for two reasons. Well, instrument air is expensive. So we want to use as least amount as possible. And then once you reach a saturation, or once you reach a water saturation point, 10% saturation, 30% saturation, wherever that number is, you don't need more air. You're fine. So this works well in multiple applications like that. Where it is limited. If you have a hydraulic system that has cylinders and your hydraulic reservoir changes oil level often, and it changes the air volume in the reservoir often, it will render this technology less effective because the airflow rate is so low. So we need to recognize that that is one of the limitations of this. The other limitation for headspace dryers is fast recovery. If you have an upset event where water has entered the system, it will clean it up, but it's the slowest technology for cleaning up the system because of the airflow rate. It will eventually remove all free water, all emulsified water, and a significant portion of your dissolved water. I want to make a word of caution with hydraulic control systems with phosphate ester. When you typically dry phosphate ester out below 200 parts per million, what we have noticed over the years is the ability for it to have micro dieseling increases because it's so dry, or spark discharge because it's so dry, and the oil itself can turn black. So we say don't dry your phosphate ester oil out to lower than 200 parts per million for that reason, but keep it in a window between 200 and 500 parts per million of actual water content, because of water reacts with phosphate ester to create phosphoric acid. So we want to mitigate and control the water content at between 200 and 500 parts per million. But there's the reason why we have a floor, so the oil doesn't turn a dark color, even though it's still functional. And we have a ceiling of 500 because any additional water above that just causes more rapid acid production, which then you have to remove through resin technology. So the headspace dryers are not limited to R and O oils only. They will work on anti-wear additives and also extreme pressure, so gear oils. Very effective and cheap. So if every 6 months you replace the filter kit for the FRL here, the membrane theoretically could last 5 to 10 years before you have to replace the membrane on the system. So airflow would be this way, in through here first, then through the membrane dryer, and then out. So this is more proper how it's shown here. Any questions on headspace dryers?
Yeah, Scott, just a little confused about that picture there. Compressed air in and then dry nitrogen outlet. Is that, how do you explain that?
I'm glad that you pointed that out because I actually am using the wrong image on this. We have a nitrogen separator as well, and that's where this image was utilized. We de-emphasized that as well. So thank you for pointing that out. It is not dry nitrogen that comes on the outlet. There's another technology that separates the nitrogen in the compressed air, the instrument air, the 78% of the air that's nitrogen. it separates that and then it dumps the other air and just directs the nitrogen into the tank. That is used very specifically for systems like, for example, a phosphate ester in a electrohydraulic control system where you may have dissolved volatile gases building up and you feel like that is contributing to more micro dieseling. We would then say use the nitrogen separator. But in most all applications, all you're going to have is a headspace dryer that just super dries the air. It does not separate the nitrogen like this is saying. So my apologies for using that. I'm glad you mentioned that so I could answer that question.
Okay, thank you very much for clarifying.
Yes. Yes, and it would not be nitrogen in here as well. If you do use a nitrogen separator for the same reason, also know that whenever you are opening your tank for visual inspection or whatever the case may be, you do need to evacuate the nitrogen out with regular air before any technicians would go into the reservoir because of health and safety concerns. In this situation, it would just be air, that's instrument air that's just been super dried, super dried.
Right.
And this is an example of how fast it can work. Then the last one talks about desiccant and what we call is trap breathers. Basically, it's just two different technologies. This works great as far as water absorbing, but they absorb and then they need to be thrown away. Works really good in conjunction with headspace dryers because it's a visual. And so you can actually dry out your desiccant breather with your headspace dryer. And so that's a great visual that you know your headspace dryer is working. There's other technology now that it allows water to be collected on the outside of the media as air is breathing in. Then as air breathes out, it pushes the water back off and it's regenerative. I don't want to get into a sales pitch. I just want to mention that there's two technologies. We recommend you use something on your systems that restricts your air interaction and kind of like a barrier for you, the humid air that interacts with the reservoir. So those are your two options right there. That's it. Okay, so pop quiz. I think there was a few questions that I have. What form of water can't be seen in a system? Dissolved water, you can't see it, but it's still there and it needs to be addressed. We think the dehydrator is better than coalesce because it works on all forms of water and all forms of oil. Coalesce works fantastic in fuel oil. It cannot be touched. So there's some areas where coalesce is really, really well. And also for fast water recovery. So some steam plants will choose to go with coalesce and vacuum dehydration on the same skid. So when they have startups, they can remove the free water really quick through coalesce technology and then switch over to vacuum dehydration for removing the remainder and then start to work on the dissolved water. And the bearing life decreases above 100 parts per million. I didn't touch on that because we're limited in time today, but consider 100 parts per million as your goal because whether it's journal bearings or rolling element bearings above 100 parts per million that start to negatively affect bearing life. All right, let's see. Last two, and that'll be it. Yeah, I gotta have enough heat.
Okay. Josh.
If I have water in a 50 gallons hydraulic power unit, what should I use? You can use water removal. But remember, just one last thing on water removal elements, water absorbing elements, they're single use. Get with your supplier and make sure that you know before you go down that road of using water absorbing elements, how many that will be needed to remove your free water. So you know before you get started, what type of investment will be needed to use that technology. So that's it. Any other questions? Any other comments?
Thanks, Scott. I don't see any questions in the chat.
I'm gonna hang up here.
People
I'm gonna
in
run
the
the
room have
bathroom. I'm gonna
questions.
get with Scott. I think he's about done.
I'm sorry, if you could speak up just a little
Yeah,
bit.
the thing is, I think Peter has raised the hand to ask the question. There is no question in the chat.
Yeah, Scott, I have a question. It may sound a little strange, but years ago I worked offshore and we had hydraulic cranes, and we used desiccant breathers on the reservoirs of the hydraulic oil tanks. And because it's a remote location, sometimes we didn't have new desiccant silicate gel beads to replace the saturated ones. So we started putting them in the microwave to boil the water out of it, and it seemed to work pretty well, judging from the color, because it turned from back from pink to dark blue. Now my question is, it seemed to work, but does that have a negative effect on the water absorption characteristics of the silica gel beads if you do that?
You can actually regenerate desiccant breathers up to, let's say, around 4 times. Where your limitation is, it's also got a dirt filter in the desiccant breather to keep dirt from entering the desiccant breather itself, and eventually that will clog and start to restrict your airflow. But we've had customers that actually would build a manifold with threaded nipples for threading on, or a slip fit to slip on these desiccant breathers, and have super dry air like a headspace dryer, and they would run the air through the desiccant breathers to regenerate them and then reuse them. But eventually your limitation will be the solid particle filter that's usually in the bottom of the desiccant breather before the air enters the desiccant beads. So that typically is your limitation. And what we've seen is if you can get 4 regenerations out of it, you're doing good. After that, you're probably going to be at the end of its life.
Okay, thanks. That's good to know.
Yeah, you're welcome. And if you on the platforms, if you do have compressed air, instrument air for use, you can always do the same thing. You could have headspace dryer exiting through a desiccant breather to keep it dry, or you could set up a little regeneration station in the mechanic shop with the instrument air to regenerate your desiccant breathers.
Okay, yeah. Thanks, good tip. Thank you.
Welcome. And if there's any other questions that come up after this, feel free to email the moderators here or myself. We'll definitely get those questions answered for you. But any other questions before we end this today?
I guess just real quick, is this there often where you use multiple systems like in parallel, I guess, or do people mostly use, say, a dehydrator, but once in a while they'll have for those upset events they'll use one of the other solutions? I guess it's all about economics, right? So,
Yep. Yeah, we have it's very rare, but we do have customers that opt to go with both coalesce and vacuum dehydration technology at the same time. And the coalesce technology is used on free water removal. So we have a sensor. Since it's saturation meter, it's limited on that. So it's more of a visual. So the technicians or the operators will be the one that say, hey, we need to go to coalesce technology to remove free water. And then we can switch it back over to vacuum dehydration. That's when I see more than one technology in use at the same time. Is steam plants, for example, very common where you would see the dual use, where it would start with coalesce because of the startup and the water ingression. And then once the mass amount of free water has been removed, and switch it over to vacuum dehydration. You don't typically see water absorbing combined with anything else because it wouldn't be needed. You know,
Right.
if I'm,
Yep.
especially with vacuum dehydration, if it's working properly, there's no free water, so it wouldn't be needed. That's a good question, though.
Okay. Well, I think that's it for now. Thanks everyone for calling in. Appreciate you calling in during your probably lunch break. We will have another speaker for February. I guess just keep an eye out in your email for the invite. And
One last thing I'd like to mention is if
Yep.
anybody has any questions, if you could just make sure that you send me those questions or you give them my contact information and we'll make sure the questions are answered. But I want to say thank you all for your time today. I hope it was worth your time.
All right, and thank you so much for giving us some of your time and teaching us about water removal.
Absolutely. Happy to help.
Thank
Hope you all have a nice day today.
Thank you, Scott.
Thank you.
Thanks,
Thank you.
everyone. Have a great day.
Bye-bye.
Bye.
Thank you.